Okay, good morning, everyone. Today we are going to do Grade 7 Inspire Science, Unit 2. The book is Unit 2, The Changing Earth. You know, what does this book name suggest? What is it going to talk about? What are we going to study in this book? That how the earth has changed. Do you think earth was always like this, how we see it today? Do you think the mountains were always there, or they were just developed recently? The rivers, were they always there at the same place where we see them today? These are the things that we are going to talk about in this book. Okay, we have to develop everything slowly to understand our earth. So the first module that you're going to talk about is module 1. It is module number 1. The name of the module is Dynamic Earth. The name of the module is Dynamic Earth. And we are going to do lesson number 1. The name of lesson is Moving Continents. It means that the continents are moving. Is it going to talk about that, something like that? We will see about that. This is on page number 6 in your textbook, Unit 2. Okay. Now, these are some objectives that you must achieve by the end of this lesson. The objectives are: what was Alfred Wegener's hypothesis? Alfred Wegener was a scientist. And what was his hypothesis? Means an idea or a claim. He claimed something. He claimed that there was something called Pangaea, there was something called continental drift. What is all these things? This is what we are going to study as our first objective. Then, when any scientist, he starts working on his hypothesis, when he suggests his idea, then he has to prove it to the scientific community that these are the proofs, so you have to accept my work. Obviously, if the work of the scientist will get accepted, only then it will be taught worldwide, or it will be used as a theory or as a fact. If just one person has an idea, it won't be you know in any way beneficial. So he started working on his idea, and he started gathering some proofs, some evidences. So one of his evidences was apparent fit of continents, which we will see. One of his evidence was related to the fossils. One of his evidence was about the mountains and rocks. And one of his evidence was about the paleoclimate. And in this evidence, we have something called glaciers in Africa. Glaciers are ice structures, and Africa is hot. So ice structures in Africa, that is a surprising thing, right? And then coal deposits in Antarctica. This one also we will discuss later. At the very end, we are going to discuss, after all these evidences, was his work accepted? We will see this also. Now, let's go through Alfred Wegener's journey step by step. Now, one day Alfred Wegener was sitting and he was just observing this map here. This is a world map. He was just looking at the continents and working on them. He was trying to figure out something. During his observation, he observed that South America, it looks like as if it is fitting inside Africa. These continents, they look like as if they fit inside each other. Can you see here? This is Africa here, and this is South America here. If I take these two continents and I put them close together, they look like as if they fit inside each other, right? How perfectly they are fitting inside each other. By looking at this continental fit, that the continents, apparently continents fit in a very perfect way, Wagner started studying other continents also. He started placing all the continents together like a puzzle. He started playing with these continent shapes like a puzzle. And when he was working on this, he saw something very interesting. He saw that all the continents, they fit inside each other. It's not just South America or Africa. All the continents, They look like as if they are fitting inside each other, or as if they are part of each other, or as if they have something to do with each other. It's not like separate pieces of land. By looking at this idea here, that all continents, they are fitting inside each other, he brought his hypothesis. He brought his idea. Now, first of all, let's discuss what is hypothesis. Now, when a scientist, he brings an idea or an explanation from his observation, which is not proved yet. He has to prove it later on by doing some measurements, by bringing proofs and evidences, by doing some experiments. Only then, when he proves his work is going to change from hypothesis and it will be established into a theory. Okay? In order to change a hypothesis to a theory, you have to prove it to the scientific community by proper explanations and evidences and measurements, experiments, lots of ways. But you have to prove your work. You have to give all the answers. Okay? At beginning, when you're just working on something, it is your hypothesis. So this one was a hypothesis of Alfred Wegener. Now let's study what was his hypothesis. Alfred Wegener's hypothesis was that all continents were once upon a time joined together as a supercontinent called Pangaea. He believed, the scientist, he believed that all these continents here, they were together millions of years ago. They were together as one supercontinent. Okay, as one continent. In other words, you can say millions of years ago, we had only one continent, one giant big continent, which he named as Pangaea. Now, then what happened? He continued his hypothesis and he continued to the idea of continental drift. He continued his idea to continental drift. Now, what is continental drift? He said that over millions of years, this big continent called Pangaea, it got split up. It got broken up. Okay? Or it got into pieces. And continents have started moving far away from each other. Continents are drifting far apart. This movement of continents away from each other or drifting apart, he named it as continental drift. You can look here in this image here. See how continents drifting? See, they are together, then they got split up, and then they are moving far away and far away. And this is somehow we are close to our world map today. This is the one. Now this one, Pangaea, broken up more, more, and then our world today. This is our world today, right? This was his hypothesis. Now again, Alfred Wegener's hypothesis was on two things. One, all continents were together once upon a time, millions of years ago, as a supergiant continent called Pangaea. Then this Pangaea, it got split up, it got broken into different continents, and continents started moving far away. And this process he named as continental drift, that the continents are drifting far apart. Okay? This was his hypothesis. Now, after developing his hypothesis, now what was the second step he has to do as a scientist? He has to go and collect evidence to prove his work to the world. So what did he do? First of all, he started collecting evidences from fossils. What are fossils? Fossils are the remains or traces of plants and animals that lived long ago. Long time ago, millions of years ago, some animals and plants which existed at that time, when they died, normally when any animal or plant dies, it is decomposed, right, by the bacteria. But sometimes some parts or some animals or some plants, they do not get decomposed. Instead, they get fossilized. Their remains are still left till today. Till after millions of years also, you can find some of their dead remains. Those dead remains are called fossils. Normally, these fossils are found in sedimentary rock because fossils are formed under high heat, high pressure in the earth's crust. That is why they are found in the sedimentary rock. Let's see how the fossils look like. This is one of the fossils of a plant, another fossil of a plant. This is a fossil of a lizard like a reptile structure. This is a fossil of a fish, and this one is a fossil of a dinosaur. Now, how did Wagner start working? Wagner started working on this creature here called Mesosaurus. This creature which you see here is called Mesosaurus. This Mesosaurus is a reptile which has gone extinct now, but it existed long time ago. We can see its fossils in different places on our earth. Now, look here. Where do we find the fossils? Do you remember I showed you at the beginning that South America and Africa, they fit inside each other very well, these continents. Now, the parts of the South America and Africa which are fitting inside very well, these parts here, he found Mesosaurus fossil here also in South America also and here in Africa also. In two different locations, two different continents which are very, very far apart from each other. He found some fossils here, half of the fossils here or half of the fossils here. Now, what does that mean? What did Wagner argue? Let's see. Wagner argued that once upon a time, South America and Africa were together. They were one piece of land. So this creature, Mesosaurus, it was roaming around on the land freely because it was one land. So they were going here and they are roaming around here and there. Then later on, they died, they went extinct, so whatever happened. After that, when Pangaea started splitting, what happened? Because of the continental drift, South America went far away and Africa went far away. Some of the fossils are left here and some of the fossils are left here. Now, Wagner further wanted to continue his argument. Now, he continued his argument and said that it is not possible for this reptile called Mesosaurus to swim all the way from this continent Africa, all the way 7,000 kilometers and go to other continent which is South America. It cannot even fly this big distance also. So how is it possible that two different continents which are so far away, which have different climates, have the same species? Some fossils are here and some fossils are there. How is that possible? It means once upon a time, these continents which are apparently also fitting inside each other, they were together and then later on they got split apart. This was his evidence number one from fossils. Now, this was only one type of fossil. He found other fossils also. Let's go and find out what are the other fossils he looked for. One plant fossil was there, Glossopteris. The name of it is Glossopteris. This plant structure here, the fossil of this plant, he discovered in many different continents. He discovered in South America, in Africa, in India, Antarctica, Australia. He found the fossil of this plant all around the continent, all around the world, all the continents, South America, Africa, this yellow line going here. South America, Africa, India, Antarctica, and then Australia. Now, today, if you look at the world map, these continents are very far away from each other. They are not close to each other. And if you try to observe, all these continents, they have very different type of climate, different weather. Africa, it is a warm one, right? We have deserts and all that in Africa. Antarctica is near the poles, totally frozen. Australia has a different type of climate. India different, South America different. So all these have different climates today. Now remember one point. Each type of plant or each type of tree, plant species, they grow in specific climates, specific weather. For example, the date palm, these date trees, we find them in UAE because this desert-like environment, hot desert environment, is suitable for the date palms. That is why you find these date palms in Saudi Arab, in UAE, in such countries, which we call the Middle East. Do we find date palms in Australia? Do we find these date palms in UK? No, we don't find them there, right? Because every plant is going to grow in the conditions that is required for that plant to grow. Similarly, this Glossopteris also requires some type of climate conditions or weather conditions. Those conditions that it requires is called the temperate climate. Now, millions of years ago, when all these continents were together, this part of this yellow line here, it must have supported that climate. It must have been in an area which supported the temperate climate. That is why Glossopteris was able to grow in South America, Africa, India, Antarctica, Australia. Okay, this was another evidence that he brought. Similarly, he brought some other evidences also. These are also very interesting evidences. Now, if you look at this one, this creature here, Cynognathus. This one is the fossil of this creature was also found here in Africa and South America. And look at the pattern here. It is found in the same exact place where South America and Africa, they are fitting inside each other. The same boundary, the boundary here. At the same location here, in this line, a very perfect line, he found the fossil of this creature, Cynognathus. If you try to look at this one, Lystrosaurus, it was also found here in Africa, and look at it, how it is found here in this small island here, and then this India, and then Antarctica. And even if you look at the pattern here, Africa and India, they look like as if they were connected from here. And at the same places he found the fossil. India and Antarctica looks like as if it was connected on these areas here. And at the same place he found that the fossil of this creature was found in the same pattern. Same thing with Glossopteris, which I already discussed. South America, Africa, India, Antarctica. It was found in all the continents. So this was one evidence that he found. Alfred Wegener's first evidence was that he found same fossil of the same species from the same age in two different continents which have totally different climate, totally different, they are very far away from each other. So how can you have same fossils from same age in two different continents? This was his first evidence. Let's go to second evidence now. Evidence from mountains or rock formation. This picture here, what does it show? It shows us an area where we have lots of mountains. You call it a mountain range. Now, what will happen if I try to split the mountains? We said that long time ago, Panchaya got split up, right? We said that the earth got split up. It was one supercontinent. So if it got split up, it means at some point in some places, the mountains must have got split up. Let's see what would have happened. If the mountains would have got split up, half of the mountains should be somewhere else, half of the mountains should be somewhere else in another continent, and we must have an ocean in between now. If it got split up, something like that must have happened. Now let's see if Alfred Wegener was able to find some evidence from mountains and rocks or not. Let's see. Now, when Alfred Wegener he started studying about the mountains and rocks, he found the same mountains from the same age, same composition, same chemistry at both sides of the Atlantic Ocean. In North America here, in Africa here, Greenland here, same mountains. You see this area here? It is marked in small dotted lines here. All these mountains here, they are made up of same type. They are same type, made up of same material. They have the same age. The chemical composition is the same. Everything is same. It's just like half part of the mountain is somewhere else and half of the mountain is somewhere else. Now, how is that possible? How can the same places which fit inside each other, the continents which apparently look like they are fitting inside each other, they have the same fossils, they have the same mountains or same rocks, and either side. How is that possible? Now, one of the real example that I will give you for the mountain correlation is this one. This Appalachian mountain range and Eastern Greenland mountain range. Half of the mountains are here and half of the mountains are here. Same mountains, but one half is in the Eastern Greenland and the other half is in USA and Canada. This one is in the USA and Canada, the Appalachian mountain range. And this one, the Eastern Greenland mountain range, is in a Greenland, which is totally in a different place. And you have an ocean in between them. How can you have same type of mountains, half of them in another continent and half of them in another continent? It means these mountains, they must have got split up, and that is why now the continents, they have drifted apart, but long time ago they were together. So he proved his point with the second evidence of mountain correlation. Now let's go to his other evidence. Another evidence was from glacier features. What is a glacier? A glacier is a slowly moving river of ice formed by the accumulation. Accumulation means constantly combining something. Constantly when there is snow on mountains, then this snow starts going down slowly, it starts moving. And when it is moving in the form of ice, you don't call it a river, then you call it glacier, because it is the ice that is moving. It's not the water that is moving. So again, glacier is slowly moving river of ice. Okay. Now let's look here. Can you see here this ice is moving here? The ice moving here between the mountains. It is now, where is this ice normally found? Where do we find glaciers? We find glaciers in areas which are very cold, freezing climate, right? So, and freezing climate is normally close to the poles. Now let's go forward and see this one. Now this car is drifting. This is a car, it is drifting here. When the car drifts here, the car leaves some marks here, right? You have seen these car drifting marks. You must have seen them on roads, many places where normally boys, they are doing this car drifting. Why do these marks are left here on the road here? Because this car is a solid and this road is also a solid. When it is moving on the road with a force, it is going to create some marks. Similarly, when glaciers, they are moving on the mountains or they are moving on the rocks, they create deep scratches. They create deep scratches in the rocks as the glaciers, they move. Now, this structure, this one, these marks which are created by the glaciers, they are called glacier grooves. They are called glacial grooves. These marks are created by glaciers moving on the rocks, or you can say the river of ice when it moves on the rock. Now, ice is a solid, rock is also a solid, but when you have a lot of ice moving on the rock, it is going to create scratches on the rock. Those scratches, those marks are called glacial grooves. Now, how did Alfred Wegener find out any evidence from glacial grooves? Let's study about that. Now, first thing was the pattern. He found the pattern of glacial grooves. See, these glacial grooves are found in many different continents from millions of years ago. Okay, from many years ago. Now, when he started studying these glacial grooves, he found them in South America here, Africa here, India here, Australia here, and Antarctica here. Now, these continents, apparently, they are the same place which is fitting inside each other. South America fits inside Africa from this part here. Africa fits in Antarctica. India's this part fits here. Australia here. It looks like it is one piece of land here which supported glacial grooves at that time. This is one type of thing, one type of evidence he said, but there is much, much more into glacial grooves. Because of glacial grooves, he got many more ideas. Let's see what is it. Now, one evidence which I was talking about is paleoclimate evidence. What is paleoclimate evidence? Paleoclimate evidence is an evidence which is from the climate of past geological age. What does that mean? From millions of years ago, the climate was different at different in the continents because continents were at different location at that time. Now see, if something is close to the equator on our in our earth, if any continent is close to the equator, it normally receives warm weather. If something is close to the poles, it has a freezing climate there, right? But these continents, according to Alfred Wegener, have moved. And if they have moved, that means the climate has changed with time. At some time, millions of years ago, the climate was something else. Then it started moving, and it went to another location. And after some time, the climate was different there. So studying this past climate from past geological age is called the paleoclimate evidence. Now, how can you have glaciers in Africa? Africa is so hot. It has warm weather. It cannot support glaciers. How can you have these ice structures in Africa? Ice structures are always there in areas which are close to the poles. You cannot have ice structures in Africa. So how can we have the glacial grooves in Africa? How? Africa is a warm continent which has average temperature of 26 degrees Celsius. But in order to have glacial grooves, you must have freezing temperatures, right? So Alfred Wegener said that Africa must be closer to the poles in the past geological age. He said that this Africa, this continent here called Africa, which is close to equator today, it is its current location. Millions of years ago, it was not here. Millions of years ago, Africa was somewhere close to the poles. That is why there were glaciers in Africa at that time. That is why at that time when these glaciers they were moving, they created those deep scratches in the rocks in the African land, and we find the evidence of glacial grooves today. If Africa has not moved, if Africa was here always, then how can you have glaciers? It's not possible. At equator we have warm climate, we have warm temperatures at most of the times. This was one of his evidences from paleoclimate. There is another one also. Let's go to that one now. Anyways, again, paleoclimate evidence. Yes, one more thing. You must understand first of all what is an equator and what is a pole. So I added this slide for you. See, this line here, this one, the red color, close to the red color, this is the equator. These continents or these areas of the continents, they are normally receiving, more sunshine. They are having a different type of climate. We call it tropical zone. Okay. And poles means this area here. The down one, blue color, and up blue color. We call them polar and subpolar zones. Okay. Again, see this African continent, it is on equator today, which means it is receiving too much of sunfall and rain. There is sunshine and rain here. And the temperatures are high. And if the temperatures are high, you cannot have glaciers. But we find glacier grooves here in Africa. How can you have glaciers in Africa? It means long time before, Africa was not here. Africa was somewhere down here, somewhere close to the poles here. That is why at that time, Africa had a freezing climate. At that time, glaciers formed. At that time, the glaciers, they were moving on the rocks. They created these deep scratches. And that is the evidence which we see today. But it is from past geological age. Okay? Now, another evidence. Do you see this picture here, the coal here? This is called bituminous coal. This coal here is called bituminous coal. It is used for creating energy. Okay, we are using it today also to create energy. Now, this coal as you remember that coal, oil and natural gas are fossil fuels, and fossil fuels are the energy sources that are created from fossils, and fossils are what dead remains of plants and animals from millions of years. So this coal is made from this plant. When this plant here, it dies, okay, from millions of years, okay, when it dies and it is under the earth's crust under high heat, high pressure for millions of years, then this coal is formed, okay. Now this plant from which this coal is formed is the ancient swamp plant. This plant is the ancient swamp plant. This plant can only grow in warm and wet region, a region where there is maximum sunshine and lot of rainfall. It will only grow there. Okay, this plant will only grow in an area which is warm, hot, and which is wet. Wet means receiving more rainfall. And from this plant, when this plant dies and it is under the earth's crust, under high heat, high pressure, this coal is formed, which is called bituminous coal. Now, what is the click here? These coal deposits are found in Antarctica. Where is Antarctica? Near the poles. Antarctica is a freezing continent, right? Africa is a freezing continent. Do you think Africa is receiving lot of sunshine and it has warm weather there and it is receiving lot of rainfall there? Do you think a freezing continent is receiving all that? No, right? But this coal is here. These coal deposits are found in Antarctica. How? The plant from which this coal is made, it cannot grow in Antarctica. What did Wagner argue? How can this coal exist on a continent which is freezing? Freezing continent cannot allow swamp plants to grow, right? So he said that Antarctica must be near the equator in past geological age. Again, if I have this coal deposits in Antarctica, if we have this coal, bituminous coal in Antarctica, okay, which is made from a plant which can only exist in warm, wet climate. That means Antarctica had a different type of climate before. And in order to have a different climate before, Antarctica's location on Earth map must be somewhere else. It must be somewhere close to the equator. Because near the equator you have more sunshine, right? So Antarctica must be somewhere close to the equator before. Then at that time, millions of years ago, this plant, ancient swamp plant, must have grown there. When it grew there and then it died, and then it was under the earth's crust under high heat, high pressure for millions of years, at that time, okay, then the coal deposits were formed. Okay. By the time Antarctica was moving, the continent was drifting and drifting and drifting, and it came towards the pole. This was Wagner's argument or his evidence from coal deposits. Now, these were all the evidences that Wagner was able to collect. Okay. So let's summarize Wagner's evidence. The first evidence that he brought was that the continents, they look like as if they are all fitting inside each other like a puzzle, right? Second one was evidence from the fossils correlation. What were the fossils that we have studied? One fossil that we studied was Mesosaurus, that reptile-like thing. It looks like a lizard. And the second one that we studied was the plant, Glossopteris. Then, third one was from the mountains and rocks. Mountains or rocks correlation. He found half of the same mountains at another continent and another half of the same mountains or rocks in another continent. These mountains, these rocks have the same age, they have the same structure, same chemical composition, but they are at two different continents. This was an evidence for him that these two continents were once together. That's why we have same mountains in two different continents which are thousands of kilometers far away from each other. Then there was evidence from the glaciers pattern that the glaciers, they were in all the continents, they form a pattern that the areas which are fitting inside each other, you find glaciers in those areas. Then there was an evidence from the paleoclimate, which was Africa has glacier grooves, which means that Africa has freezing climate in past geological age. Second evidence was Antarctica has coal deposit. Which coal deposit? Bituminous, which is formed from the fossil of swamp plants that will grow in temperate climate only, warm wet climate. This means Antarctica was closer to equator and it supported swamp plants before. It is not supporting today. Today it is freezing continent, but before it was not. Before it was at a different location. It has drifted and it came to pole now. These were the evidences that Wagner was able to collect. Okay. Now, after collecting all these evidences, now he went to the scientific community. Wagner, he went to the community. He said that, see, I have worked on all these evidences. I have very strong evidences, and he gave his work, and he wanted to build his hypothesis into a theory. But what happened? There was a big challenge that Wagner faced. Wagner had very strong evidences to prove that the continents were once together, but he was not able to explain how the continents are moving on the solid rock of the ocean floor. Now, once again, see, our continents, what are they? What is there in our continent? If you go and look at the soil and everything, what is it? We have rocks, right? Our earth crust is full of rocks. Now, if you go deep inside the ocean and you go to the ocean floor, what is there? We have rocks there also. Now, this massive continent, how can it move on the ocean floor? How can it move on the ocean? Ocean floor is also rocks. This is also rocks. This massive rock, how can it move on another massive pieces of rocks? How can it drift on it? It needs large force, huge amount of force to move on. The friction, how much it will be between when two massive rocks, they are, moving on each other. So, but Wagner was not able to explain that how these continents are moving. He was not able to explain. Even he was confused. How can continents move on the solid rock of ocean floor? There is something that was missing here. He could not explain it. So his hypothesis was not accepted. Wagner's hypothesis was not accepted, guys. Wagner, he died in 1930. Okay, Wagner died in 1930, and when he died, his work was not accepted at that time. Wagner's work was accepted 40 years after his death. Now, people, do you think they will just accept his work without reason? No, right? If they accepted his work after 40 years of his death, it means there must have been some new discoveries which led them into accepting his work. What are those new things? How was Wagner's hypothesis accepted? How all these things happened? What were the new, new ideas that came into existence? These are the things that we are going to learn in the next lesson. In this lesson, we have only studied about Wagner's observation that the continents are fitting inside each other. Then we studied about Wagner's hypothesis that yes, once upon a time, all the continents were together as Pangaea, and then they split up. Then the continents, they were drifting apart. He called it continental drift. Then he started collecting his evidences. There were 5 pieces of evidences which we discussed. Then after collecting all these evidences, the last thing where he was unable to explain was how the continents are moving on solid rock of the ocean floor. This was his challenge and he could not prove it, he could not explain it, so his work was not accepted and he died. So this is the end of the lesson. Best of luck.